Hopefully everyone is excited to finish the day and then keep going next days. And thank you all for being with us until now. It's my pleasure to introduce you guys to Arto Klami. He's an associate professor at University of Helsinki. He's the group leader of the multi-source probabilistic group. Yes, and he's also been with us since the first edition of the ProbAI school. Gave a lecture on variational inference 3 times already, I think. Two times, yeah. And a great contribution to our school. And I've had the pleasure also to work with him. So many good things to say about Arto. His research has been in Bayesian methods in machine learning, variational inference, decision-making, latent factor models, so covering a lot of interesting topics. And I guess the rest he'll show today.
Yeah. Thanks, Elisir. Can you hear me at the back? Excellent. So I'm very glad to be here and give this keynote. I'm sure Elisir only invited me so that I can talk about his work. So that's like a safe choice. But okay, what I'm going to talk about now is the choice of the prior distributions. You saw already today quite a few cases where there are some magic numbers popping up that my mean temperature, I set it at 15 degrees with certain variance. I want to help you to create better priors, so all of you. This is indeed a joint work with a lot of people. I put some of the most central names there, but it's of course actually quite many more. So to get started, I'm talking about Bayesian modeling in the exact same sense that we've been covering today. So we're building a model, defining it as a joint distribution over some random variables, the data, and all of the parameters. Once we have the model, then what we most often do is that we observe some data and we figure out the posterior distribution by means of inference. I'm not going to talk about inference at all in this talk. I just assume that we have a solution for inference, whether it's variational approximation or MCMC or analytic solution. It doesn't really matter. I'm talking about how do we specify the model. Here's one example of a plate diagram where we can identify the kind of different parts of a probabilistic model. I'm trying to use the convention that when I talk about data, I use the blue color. When I talk about the parameters of the model, the random variables there, I use this purple. And then I'm going to pay a lot of attention to these hyperparameters. So the actual parameters that are fed to the prior distribution and really define what the prior distribution is. And I try to use red color for those and denote it by lambda. What it means that once we actually, if we are kind of exact about something like the Bayes rule there, all of our results are going to be conditional on whatever we chose as lambda. So whatever prior we put into the model, it's going to be it is going to influence somehow our posterior distribution. So sometimes at least I remember to condition these results on the lambda. So I trust that you all know that this is how we build these models because you've been already spending quite some time talking about that. But now I'm going to talk really about the prior distribution. First, I want to say that there's often this kind of, you might have heard that this is where you put your subjective knowledge into the model. I don't personally kind of trust on that, believe in that kind of a basic notion. Whenever we are building any part of our model, we're already putting a lot of subjective information there. We are assuming that certain variables are dependent and so on. The prior distribution is just one component. It's just one part of this subjective choice of how do we build a model. But nevertheless, so when we talk about how do we actually choose the priors, we have 2 things to do. One is that we need to define what is the distributional family. Am I going to put here a gamma prior or a half normal prior for this positive valued constant? And then there is these kind of actual parameters that define what the prior is. So what is the mean and variance I put as a prior for this parameter? Most of the time, when we define a prior for a probabilistic model of some kind, we're going to end up factorizing it over the individual parameters. So for example, here for these two parameters, you could have one of them following a normal distribution and the other a gamma distribution. And then they have their own parameters. I'm a bit lazy with the notation, so lambda 1 here most likely would be a two-component vector, so it has the mean and variance. And similarly, lambda 2 would be having the two parameters of a gamma. And I want to start then briefly reminding that where do we need these things? And I'm going to use this kind of a dichotomy between classical statistical models and machine learning throughout the presentation. There's no clear border between these in reality, but we can still kind of imagine that there was one. So I'm going to use this orange background when I talk about classical statistical models. For example, let's say the ice cream sales model that we were just playing around with it. It's a model that's specifically hand-tuned and constructed for estimating the ice cream sales. So it's a proper model of what we are building. And here, of course, the kind of basic property handles that when we have a prior distribution, we just try to really put there our subjective knowledge of that particular parameter. And typically, you would go about implementing these models in something like Pyro or maybe Stan as the most common tool, so in a probabilistic programming language. But then on the other hand, we have these kind of classical machine learning solutions. So it could be a deep neural network, a recommender engine, a mixture of Gaussians, some kind of a general model family. It's not really designed for a particular task, but we just believe that we can fit a neural network to approximate any function. Typically, you have a huge number of parameters, and then the role of the prior. So if you put a prior distribution on the weights of a neural network, it plays a very different kind of a role that it does in a typical statistical model. We are usually doing it either for some sort of regularization type of an approach, or we're trying to somehow modify what kind of functions our network can implement. So it's not really subjective knowledge, it's just something that we encode into the model. And most of the time, you would then go and implement these on top of something like PyTorch, where it's convenient to work with these large-scale models. So I'm going to be talking about both of these cases. That's why the title of the talk is Better Priors for Everyone. So it doesn't matter whether you're a statistician or computer scientist, machine learning research, so there's something for you in this talk. And okay, so the focus is really, how do we choose the priors? And like I said, we need to choose the prior family and then choose the specific prior within that family. I'm actually going to focus on the second half here. I'm not going to talk about how do you decide whether I'm going to use a gamma prior or half normal prior or horseshoe prior or whatever that for that particular parameter. That's an important thing as well, but I just had to cut out some of the parts of the talk. So I'm going to assume that we've already somehow defined that what is our set of distributions, that there's a normal prior for this and so on. And then the task is really to set the values. So on the statistical modeling side, you would try to really bring in your best knowledge of these parameters, and you need some sort of, let's say, statistical expertise to figure out how do you do that. On the machine learning side, there's nothing like this. People just often either come up with some weird heuristics, or then much more often actually go about to using cross-validation. I try out my model with certain hyperparameters for the priors. I take a look at how well it works. Then I try it with another set of hyperparameters and always validate on some separate data that which of these is, for example, good at making predictions. So that's roughly what would be the first typical approaches on solving the problem. So I'll now then start from the statistical modeling side, spend roughly half of the remaining time talking about those, and then I switch back to talking about the machine learning models, and the color code is there to remind if you fall asleep during the first half, then you realize that when did we switch to the other. Another basic starting point is that building probabilistic models, statistical models, is actually hard. On the right, there is a kind of a systematic approach of characterizing how do people really should be building their statistical models. I think we're going to hear more about that on Thursday when Andrew is talking about the Bayesian workflow. But there's actually a fundamental problem even in specifying the prior distributions, that within this whole problem, the prior is mentioned in a lot of boxes there. So while you're building the model, you need to be specifying some initial priors, then you're going to be doing testing, then you're going to be discarding your priors, then you're going to do a bit of inference, then you again go and modify your priors to until you are happy with the model. And often this is hard. So if we look at some of these examples, it's very hard to tell that what is the effect of changing on one particular parameter. Here's an example. I just added it during the last hour. So this is the ice cream example that was there on the previous slides. And you see that there are magic constants appearing all over the model. For some of them, it's fairly easy to understand what's the effect. So mu t, I think that was the temperature. So it's usually around 15 degrees. That's fine. Alpha and beta. Why do they have a standard deviation of 100? What would happen if you put 150 there? Even if you are kind of familiar with this model, it takes a lot of time to figure out that what would be the effect of this change. Yet this is what we are actually asking people to do. We're just saying, here's my statistical model. You, as a medical doctor, could you kind of define your subjective knowledge into these prior distributions? I've never seen a medical doctor that could actually do that. I've very rarely seen statisticians who could actually do that without this very lengthy iterative process. So we need something better. I'm not happy with that kind of a choice. And hence I'm going to talk about a concept called prior elicitation. So a separate tool or software that is simply designed to dig out the subjective knowledge from a certain person that really knows the application area, but is typically not able to characterize it directly as okay, the standard deviation of alpha needs to be 100. So what we really want to have, the prior elicitation is a broad set of tools that are designed to make it easier to characterize things. So here's an animation looping where you would kind of just build this histogram type of a representation. That's what the expert gives. I believe that the parameter could be around 5 with high probability. And then it's just converted into a proper distribution. So if you have that kind of a histogram, then you can compute what would be the corresponding mean and variance for some distribution that looks a bit like that. Now I want to make a question. Who in the audience has heard the concept of prior elicitation? A few. Out of you, who have actually used prior elicitation when building a model? Perfect. This is exactly what I expected. I've also never used it myself. But we did a big study, and we really wanted to know why this is the case. So this just appeared, I think, last week in Bayesian analysis. It's essentially a large-scale review of what's happening in the prior elicitation field. And it's 60 pages together with, if you look at the reference reviews, literature review there as well. It's maybe taking a holistic look of where we are. And one of the things we already knew before starting to do this was that no one is using these techniques. Well, I'm exaggerating a bit, but I mean, they are not generally known and they're not generally used. So we tried to look into the reasons of why this is. And maybe one of the main reasons is that we don't have the algorithms. There's a long history on prior elicitation, starting from 1970s or 80s, maybe even earlier. There's a huge amount of papers actually on this, but what most of these methods are designed for, they are designed for eliciting the priors for a very specific family, for all linear models, for an ANOVA type of a model, something like this. And it really, of course, doesn't help you at all if that's not your particular model. In particular, if we believe that we now should be building all of our models with probabilistic programming languages, there is absolutely nothing there. There's no algorithm that you could just say, let's use prior elicitation now for my ice cream problem that I defined as this probabilistic program. So we don't have the methods yet. The other big problem that, of course, relates to that previous one is a bit that we have no software. There's actually been a lot of research on these graphical interfaces that allow the user to draw these distributions in different ways. But simply, partly because we don't have the algorithms for general probabilistic programs, we absolutely don't have any software support that would help you do elicitation for your particular probabilistic program. Finally, there is a slightly more vague explanation, which is there's no high-profile examples. If we had 20 science papers all using prior elicitation as a central component in their solution, I'm sure that most of you would have heard about it. Some of you might have decided to do your PhD on creating those general-purpose algorithms for prior elicitation. But there is a very understandable reason why people don't do that. So, because we don't have the perfect methods, we have some reasonably good prior elicitation methods that may be applicable for them at some point. But if you are doing your most important breakthrough of your life, you collected years, some valuable data, and you want to publish it in Science or Nature, you don't want to rely on some half-finished prior elicitation component. You don't want to take that risk. So the biggest advantage of these tools is that it makes it faster to specify the priors. But if you already sunk 2 million euros on collecting the data, you're happy to put one statistician for half a year to figure out the priors manually. Yep.
I didn't fully get what is the prior elicitation. Is it that you give, like, I don't know, gather some experts and give them this tool to specify the priors?
Yeah, well, we can play a small game here. So if I kind of take a model, this model, and let's imagine I'm the statistician, you are now an ice cream salesman. I'll show you this model, and then I start asking questions. So this mu, it is the typical temperature in Norway around this time. What would you say should be the mean temperature there? And then you give me an answer. You say it's 15. And that's like what I'm eliciting the information from you. I'm not asking you to directly tell that it's a normal distribution with mean 15 and 2 degrees. I might ask you to draw with this kind of a graphical interface that please give me a rough idea what kind of temperatures are there. And then the prior elicitation algorithm converts it that, okay, it's a normal distribution around this thing.
But aren't we like more interested in whether, let's say, how sensitive are our results, like results of the inference to this specific?
You could be. So in this Bayesian workflow part, there's a lot of checks for that. I'm personally not very interested in that. I mean, the prior is part of our model. Our model is sensitive to every single choice we do within the modeling pipeline. Prior is one of them. It's certainly going to be sensitive to it in some sense. There's actually a lot of literature on how do you recognize whether you have too weak prior or too strong prior. But I'm not talking too much about that today. So essentially, much of our big review is just pointing out reasons why we are not yet there. But we, of course, make also suggestions that how to fix this situation. There are ideas on how to do general-purpose algorithms. I'm presenting some of them today. If we had better benchmarks, better evaluation tools, and if we had the proper software, we'll actually get this process started. And one of the big reasons why setting priors in general is hard, and why many of the earlier prior elicitation algorithms are difficult as well. So the basic problem is that I'm asking you questions in terms of the parameters of the model. Some of them have very intuitive explanations like the average temperature. Many of them don't. So if you have a complex model with some nonlinearities there, and then there is some parameter that controls somehow the smoothness of some nonlinear transformation, it's very, very hard, even for a statistician, to say, if I change it like this, what does it mean in terms of my actual beliefs about this problem? It's even harder for someone who's not a statistician, so if I'm asking from a medical doctor that what would be the parameter alpha here, what should it be? So it's essentially impossible to do that well. But there is a thing that we can do. We can switch to asking questions about what do you expect from the data itself. So asking questions in the observed data space. So it's kind of a difference. So what is the standard deviation of alpha is one example where you try to directly ask questions about the parameters. Whereas, okay, you're an ice cream salesperson. How many ice creams do you typically sell on a hot day? If you're a domain expert in that field, you certainly know it's something like between 1,000 and 2,000. So what we're doing here, if we switch to asking our questions in the data space, we're going to make it easier for the domain expert to provide their actual true beliefs on what do they believe about the system. But of course, it comes at a cost. If we ask questions directly in terms of the parameters, then we would have the priors already. If we ask questions in terms of the observed data, we need to somehow convert the information we learned there back to the parameter space, the hyperparameter space. So let's do that. Here's a tool that you actually heard about this thing already in the morning. It's called the prior predictive distribution. It tells what kind of data do we expect this generative model to produce before we've seen anything. So essentially, how do you can create samples of this distribution very easily. You sample a value from your prior, and then you use conditional on those parameters, you sample an observation. And we can just keep on doing this to get a synthetic imaginary data that is what is now currently encoded in the model before we get any observations. And this is actually an important tool that is used within this classical Bayesian workflow as well for something called the prior predictive check. So what you simply do is that once you define a prior, you sample imaginary data from your model. And then if it looks horrible, if you were modeling the height of people and it says a typical height is 15 meters, then you know, okay, it must be wrong. I go back to the drawing table, I modify my prior. Here's one nice example, and it's an illustrative example of where this thing is needed. This is from the Stan documentation. A very simple model from the historical Bugs software examples, which just says, let's model the outcomes of football matches so that you have a Poisson number of goals scored by each of the teams. And then let's put a prior there. Let's put a non-informative Jeffreys reference prior there. If you then go ahead and sample match outcomes from this model, what we actually see that you have on an average around 50,000 goals scored by each of the teams. So the prior is absolutely not reasonable. It's not characterizing any information about the system. Of course, this was from an example where the attempt is that it's a non-informative prior. But nevertheless, you could easily create slightly different type of a prior and end up encoding into the model a prior belief that we typically score 100 goals in a football match. It just doesn't make any sense. But it's hard to see when you are just playing around with these kind of parameters. Hence, this is the prior predictive check is just a manual check. It still requires you to go and refine your prior. But we can actually make a prior predictive elicitation algorithm building on the same idea. So first of all, every question we ask from the domain expert is in terms of the observed data. What do you expect to be typical ranges this particular data dimension could use? Using an interface, something like this. We can change the interface freely, whatever happens to be convenient for the expert in that case. Then if we fix our hyperparameters to certain value, then our prior predictive distribution, we can just compute, either sample from the prior predictive distribution or maybe form it somehow analytically to know what kind of data the model with these prior choices is like to generate. And then what we can then do is solve an optimization problem. let's find such hyperparameters. The prior predictive distribution looks like the data that the expert believes is likely. So this is kind of we did make the problem easier for the domain expert, but we needed to introduce this optimization problem. And this can, of course, be done in many ways. So I'm just saying that let's put the expert information so that it's approximately the same as the prior predictive distribution. So there's a lot of freedom on how we actually do that problem. Here's one example, something that we did a few years ago, where we essentially start in a low-dimensional enough parameter space. You just somehow partition your data space, however you want to. If it's a univariate thing, you could maybe make a histogram. This is not from any real example, but I could just arbitrarily kind of partition this football field into these different areas, and then start asking questions, for example, that what's the probability of anyone receiving a yellow card within each of these areas? If you know something about football, you would be probably quite fast able to say that at what points, at where on the field are the yellow cards typically given. And then what we do in practical terms is that we use the prior predictive distribution to define a distribution, and then we treat the human information as noisy realizations of their true prior beliefs. We postulate a certain type of a likelihood over the human annotations, and then simply maximize this likelihood with respect to the parameters. I'm not going to go through any of the math. You can find it from the paper. So the basic idea is that, we treat human annotations as data, and then we try to fit the prior predictive distribution to make them as likely as possible. Yeah?
But this is not the data we will use for the Bayesian inference.
No, this is not the data. So what is we're still at the stage where we are setting the prior. I want to get the prior ready. Later, we're going to get data. But I'm now treating the human annotations as different kind of data simply for the purpose of converting them to a prior distribution that encodes the true beliefs of that user. So at everything, like I said, I'm not talking about inference in this talk at all. My goal is simply to find the right priors, and then you hand them out for someone else, and that someone else does the inference, they collect the data and everything.
You try to falsify the prior, like this model, right?
No, not necessarily. I'm really just wanting to get the best possible prior. That's what I want. So this is an algorithm that we did. It actually solves some of the challenges that there are in the basic things. So let's actually take a look at an example of how does it work in practice. We picked an oldish model from Lawless, which is a model of how fast male children grow. So we don't actually grow at constant rate, but around something like 13 years, there is a peak where we actually grow slightly faster, and of course, babies grow faster than older people. There is an existing statistical model for this. It has certain viable likelihood. It has 6 parameters that somehow define that form of that growth rate. Some of those parameters are easy to reason about. For example, one of them is the average adult height. Some of them are extremely difficult. So there's this nonlinear mapping age that has these parameters S0 and S1. It's rather hard to figure out what should be the value for this so that this matches my prior knowledge about these things. It has 12 parameters controlling the priors. So you need to set 12 parameters so that they jointly somehow encode what you know about these growth rates. So we did an experiment. We took very few, 5 statisticians, and asked them to use a prior elicitation interface to encode their own subjective beliefs on this. They did either the classical so-called structural elicitation, where we asked them to more or less draw what is the prior distribution you would believe this particular parameter should have. Then we also asked them to use our predictive elicitation algorithm, where we simply ask questions. how tall are 5-year-olds usually? How tall are 10-year-olds usually? And then we convert those answers back to distributions over the parameters. Here's the example. So if we just compare them, the very first parameter is the average adult male height. With both interfaces, they set this right, because it's actually kind of easy. That's a parameter that has an interpretation. Otherwise, also, they look fairly similar. But if we look at, for example, this S0, that was the parameter controlling some sort of a nonlinearity, it's actually like 10 times bigger in one of these. But we don't know whether that 10 times bigger is a big thing. It turns out it is. So here's a graphical illustration that if we now go and sample growth curves from this prior predictive distribution, with the predictive elicitation technique, they more or less match what we would expect. So now it's not the growth speed, but it really is the height there on the y-axis. On the right, we have the best possible attempt of a person trying to encode their real subjective knowledge with the direct elicitation tools, and it's just completely nonsensical. It says that 7-year-old kids are still minus few centimeters tall. Of course, if you keep on doing this, you would realize that it's bad. Then you go and revise your priors. Yeah, did I see there is a question? Yeah.
I was just wondering, it says expert probabilities. Is it one expert, or you have combined
This is for one. So this is simply one example out of our 5 experts. There's a lot of literature in the prior elicitation on combining expert information. So that's certainly something that could be done. And it actually makes things usually a bit more robust if you start combining information from more. So the basic thing is that prior elicitation, even if it's done by a statistician that kind of is supposed to believe in the model, they can't really encode in one shot their real knowledge there. You would need to end up with this iterative refinement loop, whereas in this example, at least with the predictive elicitation, we get a prior that really more or less matches our intuition of these average ages of the people. That's about the algorithm. So that's one example algorithm that is getting closer to being a general purpose thing. I didn't talk about how the optimization happens, but it's applicable to quite big range of probabilistic programs. About the software, that's simply essentially some sort of a standalone separate direction that we need to work on. We need to have software that supports take descriptions of models in arbitrary probabilistic programming language. It should be easy to launch it from something like a Pyro notebook. You just say, please define priors, and it launches a graphical interface where you can start doing it. And some of these things we can already do easily. So the way we communicate with the user, the interfaces for providing these distributions, we can do research on those even if our algorithms were not yet perfect. Here's a nice example of something that Osvaldo Martin was doing, that it just proposes a few priors and you can select that I'm happy with these. And then it forms based on these here on the bottom, the kind of real prior distribution. So we just need to keep on working on these so that we would eventually have the tools. And the basic reason that I do believe that it's possible to kickstart something like a virtuous cycle here. As soon as we have good enough algorithms with good enough software, then someone is going to realize that I need this to make my model better. I don't have time to go these iterative loops and figure out what would be the best priors. And once we have the first concrete examples like this, then of course it encourages us to again keep on working with more general and better algorithms. Maybe they're able to release some sort of a benchmark data that makes it easy to work on these. So I have one task for everyone in the audience. So whenever you write your next Nature paper, remember to use prior elicitation. Then it kickstarts this whole thing because someone else here then knows that I can make a better elicitation algorithm for this kind of models. So just remember to do that. Let's then switch to the machine learning side. So if you absolutely hate these these kind of well-defined statistical models and want to play around with something like deep neural networks, we can do pretty much similar things. So the parameters no longer have any reasonable meaning if it's like, for example, really neural network weights. And what people do in Bayesian machine learning community, there's a lot of these lazy researchers who just say, I don't care about this parameter. I just put it at 0.1 because the previous author did the same and I was too lazy to try out other values. I kept on doing that for years myself. And then, of course, a lot of other people would just say that let's do cross-validation. Let's partition our data, fit our model on one subset of it, and evaluate how well it works. Can anyone guess what's the big problem with the second approach?
The bigger your model, the more expensive it becomes.
Yes, it's expensive, and it's really expensive. And the big thing here is that it requires running inference. So you try out training your model, maybe some large language model that takes 6 weeks to train. You try it with one set of hyperparameters, then you do it again with another one. You always need to do the inference. So the bigger the model, the more data you have and so on, the slower it gets. So we definitely don't want to do that. What we actually want to do is have an algorithm, a system, pretty much like the prior elicitation that I just talked about, that allows you to choose these hyperparameters without doing inference at all. And the starting point is the same. We have the prior predictive distribution. For any lambda, it defines already a probability distribution over the data. We can sample from that. We can usually compute some statistics of that. And I argue that we can actually figure out good hyperparameters for a model without ever learning the model, which is kind of counterintuitive. So if you think about any other modeling approach, it sounds like a holy grail that if you would be able to do deep neural networks without any sort of a cross-validation system needed for tuning any of the architecture and so. But luckily, Bayesian models have this generative property that gives us an extra tool. So it's an opportunity to do something that you could not do without having defined your model like this. So I put there the details for, this is the part that I said that I'll talk about Eliezer's work. So we have a paper, it's again a 50-page paper, so it takes a while to read, where we talk about this principle in the context of matrix factorization. So our choice of Bayesian machine learning model is matrix factorization, but we talk about many of the things that we talk about in that paper generalize to other cases as well. So this is the basic idea. So first of all, we choose some statistics that we care about, statistics about the data. Let's say we want to be getting such hyperparameters that the mean and variance of our observed data is characterized well. Then we can take our actual real data, the same data that we are going to use when we start doing inference. I can compute the statistics from that data. And then I can solve such hyperparameters that the prior predictive distribution generates data that satisfies the same characteristics that the real data has. It's the same mean value, it's the same variance as in the real observed data. Any problems with this? Does it sound like a valid Bayesian procedure? Okay, I'll get back to that soon. Yeah. Now, there are people, like our reviewers in that paper, that would say that this is actually cheating. We are looking at our actual observed data while we are still setting the priors. In reality, it doesn't matter at all. If we only, let's say, if I had a matrix factorization with 1 million observed entries in my matrix, I'm not using that whole data. I'm just computing from that data what's the mean entry over these cells. It's almost the same as if I had just normalized my data slightly differently. So I argue that there's absolutely no risk of double dipping to your data. But if you insist, you can, of course, take a separate validation data, compute your target statistics from there, and then everything is fine. Or you can even ask them from an expert sometimes. So this is what we're going to do. The distance measure, I'm intentionally skipping it here because I'll first talk about an approach where we don't need to choose it. we are actually going to be able to perfectly match them. So any distance measure that becomes 0 when they are identical would be enough. Other than that, it would typically be something like a mean square, let's say squared Euclidean distance or something. But it's a free choice. So I'm going to give you an example in this family of matrix factorization models. In particular, I'm talking about Poisson matrix factorization and its extensions. So we have an observed data matrix. It could, for example, be how many times you listen to a certain song in some streaming service like Spotify. So it's real valued counts. No, sorry, not real valued. It's integer counts. And if you look at this model, so there's always going to be this kind of a k-dimensional representation for each user and each song. We take an inner product of those, and then that becomes the rate parameter for a Poisson distribution for one of the matrix cells. The priors are here these f functions. So we have a prior for every entry in theta and every entry in beta. We're going to make them independent over all of the entries there. It's written here with the character f instead of any particular distribution because what we're going to show, it actually doesn't depend at all what the family of prior distribution is. You can choose whatever you want. You're going to still be able to use our technique. So we're not restricted for something like conjugate priors. And like I said, there are certain cases where we can do this very efficiently. For Poisson matrix factorization, it turns out that we can analytically compute the mean value, the variance, and certain correlations between the entries in the observed data matrix. So we don't actually have to solve, and then once we give like an analytic expression to those, we can directly solve that analytic expression such that it becomes the statistics, the target statistics and the prior predictive statistics become exactly the same. So we can, without spending any time, immediately by simple analytic expressions, set optimal hyperparameter values. That's quite a bit saving compared to running Bayesian optimization. Of course, this is tedious. So we're taking a specific model, we're deriving analytically by hand certain moments of that prior predictive distribution. The best way to do it is just host a visitor who wants to do pen and paper exercises. So if you need this for any new model, just ask Eliezer. He did it for Poisson matrix factorization and actually for a very broad class of its extensions. So what we can do is, we can take a look at, for example, the data matrix Y, any given entry in that data matrix. In the prior predictive distribution, the mean value is going to be k times the mean of both of the priors. This is actually not a very difficult thing to solve. It's two k-dimensional vectors that we take an inner product between those, and every entry in both of these vectors, on average, is characterized by this mu. So the mu was the prior mean here. The mean is trivial, the variance is quite easy. Then at some point we realized that we need correlations between two entries on the same matrix row and so on. But it can be done. And once we've derived these expressions, we can actually start doing the kind of learning the prior. So we compute from an actual observed data matrix these means, variances, and correlations. And then we do algebraic manipulation. So what we get as a result is, for example, a closed form expression directly telling you that if you're going to do a Poisson matrix factorization, how many components you need to have in your factorization. That's been, in general, like an open problem in factor analysis models to figure out how many components do I need. We get a closed form analytic solution for that. This is for Poisson matrix factorization. For the other matrix factorization models, it's something slightly different. But it still can be done. So this is not really maybe even a prior hyperparameter in the same sense as everything else is, but it's still. And there's other results. So we can also say that what should mu theta, mu beta, and so on be. If we test this on an artificial data, where we generate data from a Poisson matrix factorization model with some number of components, put that on the x-axis, on y-axis, we then have the estimated number, how many components the algorithm proposes you should be doing, and it matches perfectly when the model is when the data actually comes from that model. In the paper, we have lots of other extra experiments that show, for example, that how does the accuracy start degrading if you have, for example, over-dispersed data and you're still modeling it with the Poisson matrix factorization. But it still has very, very good results there. And now really the basic gist of why do we need this is that it's fast. So this is an example that we did on some relatively small Last.fm data, that is these counts of how often you listen to something. We picked intentionally a very fast variational approximation as the inference problem. And then we started doing Bayesian optimization to estimate the best possible hyperparameter values. The x-axis goes here to 1 hour. Yeah, this is seconds, so 3,000 seconds, whatever it is, yes, 1 hour. What we see is that eventually, if we keep on running Bayesian optimization, we are going to have such hyperparameters that it's probably a better model for some sort of a predictive task. But at the point we have been doing this for 15 minutes, we would still be having by far the best solution with this immediate analytic solution. This was in a case where it actually is fast to do inference for the model, but if it took 3 weeks to run your model, you just don't want to do the Bayesian optimization there. It's going to be lots and lots of computational resources for that. And of course, if you're not satisfied with whatever accuracy you got with our analytic expression, you could, of course, put that as a starting point for Bayesian optimization. So it certainly helps to compute that as first. The big problem here is that this really did require the analytic derivations of all the means and variances and correlations, and it is a bit tedious. We also proposed in that paper another algorithm that is kind of a standard stochastic gradient descent type of an optimization. So now we actually do need to, yeah?
I had like one generic question. Now we are trying to find priors, like to have semi statistical reality.
Yeah.
Like when we are estimating the priors, or when we need to put the prior in such form that our model can quickly go in different directions when we actually will be doing inference, and can we like somehow enforce it?
It in principle could. So yes, if you would, in some conditions, you might end up defining way too narrow priors, and then your data wouldn't be able to influence it. I would think that that would usually happen only in the kind of cases where you give very detailed information as the statistics. So if I, for example, set only the mean, I just say that I'm going to have an average 5 times people listen to each of these songs, it leaves a lot of flexibility on what the parameters could be, and the actual priors that it proposes are quite broad there. But yes, there is some risk of that. That's a very good point. But okay, so if we can't do analytic things, the good thing is that we can always sample from the prior predictive distribution. Then we can take any sample that we got from that prior predictive distribution, and we compute the same statistics from that sample, which we can then compare to our target statistics. If we use the reparameterization trick for the gradients, which I believe you will probably be hearing tomorrow about, yes, so I don't talk about how it is done. So we can actually then just use standard gradient descent for optimizing this, for arbitrary choices of the distance measure, for arbitrary choices of the statistics. It's no longer immediate. You don't get an analytic solution right away, but it's typically very fast. So here's an illustration that if we, for the same Poisson matrix factorization for which we actually have an analytic solution, if we intentionally try to solve it with gradient-based descent, it takes around 10 to 100 seconds to find this solution. It's still way faster than that is 1 hour that the Bayesian optimization was taking. There's also some extra tricks that you can do. So if you, for example, evaluate from your actual data the means and variances, put them as targets, and if it's impossible to simultaneously satisfy both of those with the Poisson matrix factorization, we will recognize it because the discrepancy doesn't drop to 0. And then the practitioner might actually say, okay, I need to go and change my model. I can't model this with Poisson matrix factorization. So maybe it's over dispersed. I need to do a bit of a model changing. But that's kind of more or less general. So it's applicable to all at least continuously parameterized models and some others as well. So that's actually everything I had now. So I'm just going to remind you about the basic things that I told. So we were going through the case of how do you actually choose the hyperparameters that define your concrete prior within some pre-chosen family of prior distributions. If you look at the statistical models, I argue that the direct specification of the parameters, either by just manually writing them or even using these old structural prior elicitation techniques, it's essentially impossible. It's really, really hard. The prior predictive elicitation that asks questions in the observed data space, to me it looks like that we are actually now starting to have the algorithms there that works properly, at least for low-dimensional enough observation spaces. I mean, in the classical way, you need to do separate elicitation for every parameter, or now we need to do elicitation for every dimension of our observed space. But we still need better algorithms and software, and especially the killer applications, so that people actually believe that this is a tool that they need. Otherwise, no one works on them. On the machine learning side, I think this is actually a fundamental result. So there are categories of models for which we can automatically choose the hyperparameters that define how the model works. We just need the prior predictive distribution and some analytic tricks. If it's not a Bayesian generative model, none of this applies. So you can't take a support vector machine and start figuring out how to select its hyperparameters. We have very fast, either immediate or fast gradient-based solution, and we don't need to do inference at this stage at all. The main problem on this side maybe is that we talked intentionally about Bayesian matrix factorization models because they're unsupervised models. It's just enough to characterize how does the data look like. But if we have a conditional discriminative model, you're going to have lots of different inputs. We need to somehow decide for which inputs we ask the expert or compute from the data that what the statistics for the output should be. But that's something that we are kind of starting to work, and I don't see any unsolvable problems there. So I think there is hope that also for those types of models, we will get similar tools soon. And then the take-home message. So what I want you to do after the summer school is kind of either work on, create these general algorithms. Give me a universal prior elicitation algorithm that applies for all probabilistic programs, or then just use prior elicitation whenever you do your breakthrough application papers. I still put there's some references, I can put them there on the background, and I'm happy to take still some questions if we have 3 minutes remaining, I guess. Anything? Oh, over there, yeah.
When you use humans to evaluate the probabilities, and say, well, you have a number of experts, and each of them could have different opinions in the way, like, do you foresee like the tails will be much more discrepancy in the tails than some kind of like me, or I don't know, having the experience using several people for the evaluation of this outcome?
I think it would need to be part of the software. So I haven't worked personally on this topic of integrating different human experts. I know that there's research on things like how do you aggregate them? Or also from the perspective that is there within this pool of people, is there someone who actually has a substantially different prior beliefs about this problem? It could be, for example, that that person is not really a real expert in that field. So we could also use this to educate people, essentially, that you try to encode your prior information and then you see what comes out of it, and then that's kind of a trigger for you to start thinking about a bit more how do these things go. I don't think I have anything else to say about that. Yep.
Can I ask how all of these connects with empirical base and people that use the data to form their models?
Sorry, I didn't quite.
So I've heard that some people use the data to decide about the priors
Oh.
or empirical base and things like that. How does that?
Yeah, so at least I think there's a concept called empirical bias, which is pretty much exactly that you compute something. This is very much related, so I would say that this is a subset of empirical bias method. So in empirical bias, usually you do some sort of maximum likelihood estimation for some parameters there. It doesn't really build on the use of prior predictive distribution or the target statistics in that sense, but we actually talk about that for like half a page in the paper, trying to outline the connections. Oh.
How do the priors that you come up with using this moment matching approach compare to the Bayesian priors? Like they have, say, like the optimal Bayesian priors?
Let's see. What's an optimal Bayesian prior?
The graph you showed sort of on predicted performance.
Oh, yeah. You mean this, yeah.
And then I guess this also connects to ongoing research. Like what aspect of the elicited prior is most important to carry over? Like the moment matching, the same support, symmetry. Is there any sort of
We haven't really thought about it, so I don't know, for example, here, I don't think whether we ever looked at that what is the real prior that we are inducing by this. Especially on the machine learning side, we mightn't even care. We're happy if the predictive performance is good. Ultimately, yes, the more of these different types of statistics you try to feed into this algorithm, let's say if you go too deep, then you are starting to be at the point where you're already kind of using your actual data at this stage before you switch to inference. It would probably be better to use the data at the inference stage. I think also the risk of the prior becoming too strong may grow, but this is something that we haven't really studied properly. There's the one, yeah. Yeah.
About how video even how do you feel like some kind of overconfidence by having this? And as in, for example, here the prior I guess
No, the prior optimal is the dashed line there. It's the whatever we get from this algorithm. So overconfidence, it's certainly possible, yeah.
I was wondering about selective prior, that it's kind of an interpretation of the model, but then the model, it can be I don't know, if the priors get too much overconfidence, then at the inference time you get this profuse.
Yeah.
Which is very hard, because of, and then you're like kind of stuck in this flow of and the second question, sorry, was like in the optimization problem where you define the RFE.
You mean this?
When it comes to the practical problem, how do you define the T, star? And what is the sense of time?
Yeah, okay. So for the first question, I think there is, if you do use these things naively, you might have a risk of going to too confident priors. But we could, of course, also explicitly encode some sort of additional constraints that we really actually want the variance to be big enough or something. But that's something that would need a bit of more research. Here, so the T star is you take the real data, you just compute the mean and variance of all the entries in the observed matrix. So it is simply, we've just chosen that we use mean and variance and correlations, and we just compute them from the data. And then the T X conditional on lambda, that would be we compute the exact same statistics from the imaginary synthetic data that we sampled from the prior predictive distribution. And then we just compare those and try to minimize the distance between these. So the T star is the target. That's the defined by the observed data. And then the other T is what the model is currently spitting out. Yep. Specific choice of the statistics, or the distance measure. In the analytic solution, we will get exact match. So in the ones that Eliezer derived. So the basic idea here is that we really get these analytic expressions that if you apply those, then the statistics will be exactly the same. So it's any distance measure that every proper distance measure is 0 when they are the same. But then when we talk about gradient-based optimization, we have to postulate some distance that we are happy to minimize.